Okay, uh, we are keep going through another example of defining a connector within SolidWorks. So if you go to folder of the shared material, now open the folder called bolt connection. And here, if I open the problem statement to understand that what we are doing. So we do have two plates that there is a vertical plate and a horizontal plate. Let's call this gray plate as a support plate and this blue plate as a loading plate. These two plates are, so the support plate thickness is 10, the loading plate thickness is 15 millimeter. These two plates are fixed together in a pattern of the four bolts and nuts. It's given that the bolts is M16. So this is two bolts here, two bolts here, four bolts in total. There are some geometry definition of how these bolts are defined, how they are located. And it says that all fasteners are medium strength steel and are torqued 20 Newton meters. It means that the fastener, which is the bolts and nuts, are made up out of steel, medium strength steel, and they are preloaded with this 20 Newton meter torque. It means that when they are fastened these two parts together, they applied a 20 Newton meter torque. So they are tightened this bolt with 20 Newton meters torque. Uh, then what problem wanted to see is if we apply 16 kilonewton force downward at the very end of this loading plate, we wanted to know if the structure are okay, if the bolts are selected properly, how we can optimize these bolt and fasteners for this setup. And also it says that the material is alloy steel for these two plates, except these fasteners. Okay, so I would like to open a assembly file. I have already modeled these two plates, as you will see. Okay, you will see here that this is, let's make it a little like a color. So here is the one that we had as a supporting plate. I would like to give it a color of light gray. So like this, for example. And this part, let's give it a, okay, let's define a loading plate. So the loading plate, appearance, loading plate as a light blue, like similar to, there you go, maybe a little better. Okay, and the holes are defined, they are concentric, and everything is okay. So as you may guess, we don't need to really model and, for example, define it by the fastener or smart fasteners here. SolidWorks can do the legwork and do the simulation more precisely and accurately, and it's highly suggested that we go with the way that SolidWorks defines the connector rather than you actually model and put the bolts here. And that's what we are going to do. So before doing that, something that I would like to discuss about, a database of the fasteners, how in industry those fasteners are been defined. We discussed about the fasteners in the previous class. So there is a very good website that kind of I wanted to use that information in conjunction with this simulation that I'm going to do and not simply accept the default values that SolidWorks suggests for that. The site is McMaster.com and it's a McMaster car and it has a very large database, very accurate database of a lot of fasteners and small parts here and there. And uh, here is the fastening and joining. For example, I would like to, here in the problem says, all the, or was that? Here. It says that all fasteners are medium strength steel. We want to know what does it mean. So let's select a hex bolt because these are all hex bolts, right? I'm going to go to screw and bolts here, for example, and it lists all the possible type of the fasteners. I'm going to with the hex head screws, for example, and here you have a variety of the selection of that, but now you can do the filtering here to reduce the number of selection. For example, here the problem says M16, so M, it means that it's metric, right? It's not the inch system. So I would select the system of measurement as metric, and it says M16, I would select M16. The length is not that much important, so I can move on from that. For example, I select 2 millimeter as a thread pitch. It means that if each thread has 2 millimeter distance from the next thread. So 2 millimeter would be the pitch, fully threaded. And here it says we have different things that we can select. And now it's pretty much filtered enough, and material is a steel, so we can go in that way still here. And you see that there are some selection it's given here. It's a high strength metric, medium strength, and left hand extreme strength. So obviously we have to stick to this one. So there are multiple finishes here, not that much important. For example, I would select, and these are all coarse thread. And if you see here, for every part that you may select is going to, for example, select, this is like a 40 would be the length of that. So if I click on here, here says product detail. Not only you can download the SolidWorks model of this one if you need, which you don't have to, but if you wish to know that. And here's some good information is given here. For example, this is hex, this is metric, M16 2 millimeter pitch, the length is fully threaded, coarse. And then if I'm going all the way down, and this is the material I selected, it says that the tensile strength is 10,000 psi. And I would like to use this information, a real information of these fasteners in my simulation rather than, different. And of course, if you go back and select the different properties, you have the same set of the information that you can use. And this is highly valuable to really use a data sheet and the real spec of the material rather than sticking to the default. And I will show you how to use that. Let's go back to SolidWorks, and we will get there. So I'm going to go to simulation and start a new study. And here I will select bolt connection and hit OK. Then a simulation panel would be readily available here. The parts, first we need to do that, and it says all of them are alloy steel. So select part, right click, apply material, all. Do we have alloy steel here? Doesn't have that. Let's go here. So in the window of that, it would be alloy steel here. Selected, apply, close. So material has been successfully defined. So there are some additional steps that in this model we have to how we define the bolt here. For example, let's select defining a bolt. I would right click, and from here we cover the spring and pin. Now we select bolt. Waiting for the window. Okay, it's selected, and now it defined what type of the bolt we have. We are going to do that. This is like a counter bore bolt and nut that we are going to define. So we'll stick to this one. Then we have to give them two edges for that bolt and nut to be defined. So the first would be this one, and we'll select the second one, and then coming all the way here and select the other side. So two will be selected. Now SolidWorks know that the bolts and nuts should be defined across these two edges. So here it says 16, so the shank is 16, and if I go back to the way that it's been defined, it should be accurate because you will see that here is 16, this diameter here. Even if you go to, yeah, the diameter would be 16. And now this distance is given at 24. SolidWorks by default select this one 1.5 times of this. So if your spec says different, you can modify it here. Moving down, we are selected distributed. It means that the face of that, it means that this face of the bolt would be distributed evenly on this face, so it's more realistic in the information, in the analysis data. Material, it says alloy steel. Now we can select a different material that is given here. I think it says medium strength. We can define it in the strength data, so we can stick to alloy steel for this point. That should be fine. And then you're going to the strength data, and that is the part that you have to give them some definition. Unless you know the known tensile stress area, you have to select this one, or we can calculate that, and that's the one that you have to do that. First, here is the pitch. So the pitch was 2 millimeter of the pitch. It means that it's half a thread per millimeter, right? Meaning that in each millimeter there is half of thread. In the 2 millimeter there is 1 thread, which is definition. Now here it says, here in the strengths, it says tensile strength is 110,000 psi. So I'm going to here, select it psi, and I would change it to 110,000. That's a bolt strength. And now this is a safety factor of 2, similar that we do. And here is preloading. And as the problem says, it is 20 Newton meter, meaning that these bolts and nuts, they are torqued and fastened together by 20 Newton meter torque. So we are good, but before hitting OK, we are going to define the other. So I'm going to pin here, and I'm going to select other doctor. Here, hit OK. That's a very typical mistake that it's very common. So I have to select here, select the other field, and then select here. Hit OK. And the third one. And you will see that all of the definition would stays in place because that's sort of a group definition for all of the fasteners. It's going to save time when you are defining a group of the connectors. So here, select here, and of course is that same head for same head and not diameter, meaning that diameter of both should be the same, which is typical. Hit OK, and then all of the 4 has been defined. I don't need to define 5th, so I hit cancel, and you will see that SolidWorks actually put this bolt and head here. So the length is not in question. The length of the bolt is really does not change the analysis result. That's why it never asks what is the length of that. But the point is, when you see these blue connectors, it means that SolidWorks successfully defined the connectors the way that they are supposed to be. All right, so we still have something to do here. Similar to if I go to the group, like interaction is bonded, meaning that no penetration between the parts. However, I have to define a local interactions because I wanted these two parts, this face and this face of the parts to slide with respect to each other if there is any like a force between them, and I have to define it. So in order to do that, I would right click on the connection and go to local interactions. And it means that by local interactions, I want to define the interaction between these two parts. I'm going to, instead of selecting manually, I would select automatically. And here I would say, what are the components? I select this one and this one. and then they can find the local interactions by finding the faces here. And it found that this face and this face is part of the local interaction. You could have selected manually, give them these faces, but this is another method. And the type is contact, meaning that at all times these two faces should be in contact with each other. Then I would say hit OK. Do you want to create local interactions? Yes. And here's that local interactions that has been defined. Okay, so now I have to define a fixture. So I'm going to go select the fixed geometry. And since this is like a fixed part here, this plate, I would select the back of that as a fixed part. So that would be the fixed part, hit OK. I have defined a sketch part here that can be used, and I think this one maybe has been splitted, or yeah, there's a split line, which is I can use that for essentially how to define that plate. So for the loading, I go to external load, apply the force, and this is the area that the force should be applied. This is like a split line that I already defined here. And then here you would say was how much was that? 16 kilonewtons. So that would be 16,000 newton. Direction is correct. Hit OK. Now we have the direction here. So just check on it. We have defined the material for these two plates. We have defined a 4-bolt connector, bolt and nut connector. And we defined the local interactions to keep two faces always together. These two parts would be always in contact with each other. We defined the fixture and external load. Now we can go and create a mesh. I would come it to a little fine here, define it. So 2 parts, and SolidWorks start meshing that. Okay, we should be ready to run the analysis. And essentially, we are trying to give the answer that if the bolt that we selected is optimum for this design, it means that if the pulse is a correct selection for this assembly, are they going to survive, and are they going to meet that factor of safety of 2, which is like a 200% safety, one additional 100% safety margin for the factor of the safety for each bolt. Okay, this may take a while. Okay, I guess I can pause the video and resume it when the simulation is over. So I will go back when it is done. Okay, the simulation is calculated. So first off, you will see that these two parts are successfully past this loading. The yield strength is 6.2 10 to the power of 8, but the maximum 1 meter stress that has been calculated is around this edge with a value of 2.8 10 to the power of 8. As a matter of fact, I can define a factor of safety, right? But as we know, this factor of the safety plot would only applicable for these two plates, for these two rigid parts. They don't include the connectors. But let's see what is the factor of safety of this design would look like. So you will see that the minimum factor of safety for this design, for these two parts, are 2.17. Very good and successful design. And some areas has the larger factor of the safety, but the minimum is 2.17. If I go to displacement, for example, I can run the animate to show how this look like. So this is very small displacement. It means displacement is true scale and it's not the exaggerated one. So I go to edit definition of the displacement, for example, and instead of true scale, I would select automatically, which apply a scale factor for the displacement. Now, you will see that how these bolts are really under motion. First of all, it shows the rotation of this, meaning that as a result of this motion, what is the possible rotation of these if they are going to get loose. And but you will see that there are some motion. But again, this is an exaggerated motion because the real displacement, the real max displacement at this end is about 0.6 millimeter. So that's an exaggerated motion, but at least show how these connectors are subject to the displacement as a result of this force. So now let's jump into the answer of the question, are the connectors okay for this design? And in order to do that, as you know, we are going to right click on this result and go to define pin/bolt check plot. So if I select that and hit OK, the answer is negative. It means that these bolts did not pass the factor of safety. But let's see what is the factor of safety for each. So the bolt number 1 here, the calculated factor of safety is 1.67. Actually, we can find the critical bolt here to see which one is the most critical. So that was 1.67. Bolt number 2 is 1.12, smaller. 0.3, 1.68, and 0.4 is 1. So this is the critical bolt here because the factor of safety, the calculated factor of safety is the smallest for this bolt. And after that, this, and then these two bolts. So essentially, in a nutshell, these four bolts, all of them fail to provide the factor of safety for desired factor of safety of 2. So I wanted to know that what is the solution for that as a like a engineer if you wanted to provide a solution. For example, let's exercise the option of selecting a different material for this bolt. If I look at the MagMaster car and here, instead of material, I will select the steel material, or instead of selecting the material, let's select the steel but going with the highest strength. Same material but highest strength. And here you will see that the stylus strength for that is actually 150,000 psi. So let's do that and let's see if this is gonna bring any different result if I change to from 110,000 to 115. So here it would be 115. You have to select one by one and update those. Okay, so all of the materials are 150,000 right now. So let's run this study one more time. I would pause the video and go back after the calculation be completed, because it takes fairly amount of time. Okay, we're back. The result of with addition of with the different bolts. Let's go to pin and bolt check. So you will see now, interestingly, 2 bolts are okay. 2 bolts now are green, but the other 2 is still, the factor of safety is been a little bit increased, but not reaching 2. So that was a good example of showing that how selecting a different material or different properties of the bolt may satisfy the design condition. So hopefully you learned something about this defining a bolt in this example.